Well, thank you, Chris. And I'm Lou W4LT, and I hope I don't confuse you too much. So anyway, we'll get started with stuff like this. So here we go.
Please copy number 11. Please copy. Please copy. Please copy number 17. Please copy number 10. No, please copy number 1 and 6. Please copy 005. Please copy. Please copy number 009. Please copy.
If I ever hear one of you guys say "please copy," I'm going to deduct the points from you. I hate that, and I have no idea where it came from. But this "please copy" stuff is just ridiculous. So don't do it because Dr. Decibel is going to come after you with his ready snitch. Okay? Don't ever say "please copy" if you know what you mean. Anyway, all right. So I'm not a reader of PowerPoint, so I'm going to assume that you're going to read the PowerPoint uh, things that have up there. I'll read some of them, but not most of them. But one of the keys to this is you can spend a lifetime studying this subject, and I got an hour to do it for you. So strap in, put your seatbelts on, and let's get going because away we go. This is the stuff as we're going to talk about today. Especially one of the key things is ALC, and the other one's going to be EQ, compression, noise, and gaining. What are they? Because a lot of folks don't really understand how all that works, especially the ALC thing. And you hear a lot of splatter. A lot of the splatter is caused by that. And I'll explain to you how that works. But the first thing we need to do is we need to discuss about the composition of the voice. What is the voice and how we make the voice work. So if we don't know these basics, that then you can't really understand why you're doing what you're doing. So different voices are of course different, but some are more different than others. But basically, this is how it works. Okay, there was a really bright guy. I don't know if you guys know about him. His name was Shannon, and Shannon he worked at Ma Bell back in the 1930s, and he was
Claude.
tasked. What was
Claude.
that? Claude Shannon, but he
By the
was
way, his
hmm,
paper is readily available on the internet and it's very easily readable and
yeah.
understandable, and I recommend it.
Yeah, it's great. But anyway, back in the 30s, he was tasked by his boss to figure out how to make voice transmissions go through the phone system easier and simpler and make them easier to understand. His studies, they formed the basics of acoustic research in communications, frankly. And his basics found out what frequencies are used by human speech.
This meeting
And
is being recorded.
oh, well, thank you so very much for letting me know. All right, but anyway, his work is seminal information by recording, playing, and moving content through readable electronic devices. Things like MP3s are based on the psychoacoustic stuff that Shannon came up with.
Okay,
And
there you go, Owen.
hello,
Okay, talk to you later.
somebody needs to mute. All right. Anyway, human information is transferred and centered on a small group of frequency ranges. Note that these frequency ranges overlap and they mix because voices are really complicated things. So as you can see, our consonants, vowels, and fundamentals, that's what Kenwood calls them, of the male voice, and we're going to talk about the male voice, 85 to 250 hertz. So the lowest energy and power content from those, but they're rich in harmonics, so the harmonics climb on up the into places that give you punch and give you understanding. Um, Multiple redundant frequencies use up the spectrum, so that's how it spreads out. Vowels go from about 350 to 2 kilohertz. They have the most energy and power, but they have low harmonics. So they contain the most information, so they get buried by some of the consonants sometimes, and that causes you not being able to understand what people are saying. And of course, there's consonants. They go from 1 to 2.5 kilohertz. They use the medium energy to transfer the rich harmonic content that they contain, and they are critical for intelligibility, and that's a key word, intelligibility. It means people understand what the hell you're saying on the air. So that's the key to that. Vowels have the power of the voice, and consonants provide intelligibility. Remember that. So if you tailor the message spectrum over a closely defined and limited frequency range, Intelligibility can be managed for a minimum loss of fidelity. So yeah, it doesn't, if you look at that back there and you see the spectrum bands that contribute to intelligibility, you add them up, they're 97, not 100. And the reason is called entropy. If you know what entropy is, that's adding noise in the system. There's noise through the amplifiers. There's noise in your ears. There's noise in your voice. All that stuff is about 3% of this stuff. So that's the entropy part of communications. So the less channel noise, the less ambiguity to discern intelligibility of the content. So now let's play around with the vowels here. This is a really great chart. Notice it doesn't take into account some languages. Like if you're talking to a guy from Zimbabwe and he speaks Swahili, you'll hear a consonant that goes like this. Well, that's not something that we know of. But anyway, I digress with that. So what it sounds like, let's take a listen to the vowels and see where they fit, and listen to how this works. The letter, we'll go with each letter. U, O, A, E, I, and we won't do sometimes Y, but no one won't worry about that one. Okay, so they're basically the power of the spectrum is concentrated between 200 hertz and 3 kilohertz. So where have I seen this before? Where have you seen this before? Okay, essentially for communications quality audio, here's where we need to end up. Anywhere from 200 to 3150 is the key place, because if you notice 3150 is right at 9%. Okay, so look at that rising curve and you tell me, hey, we set our radios to work like this. Does it look familiar? So now let me tell you this. If the only thing you do is set your equalizer on your transmitter to look like that curve, you're halfway there. Okay? You'll notice that there's a dramatic increase in intelligibility on the HF bands if you do this way, because what you're doing is you're concentrating the power of the parts of the speech are going to let people understand what the heck it is that you're saying, and not worrying about the rest of the bandwidth. It doesn't really help you. Now, there's a difference between male and female voices. You've heard women on the air, right? Man, those girls are great. And I would suggest that everybody who has a team of multi operators have at least 2 women on it, and those are going to be the ones that are operate on the second night of a 48-hour contest when you need to get the most points and get the most pileups going, because their voices really cut through. To take a look at what we have here. Female voices that have a definite advantage in speech communications. Why? Because of the way they're set up. If you look at the female voice at the bottom and the male voice at the top, here's a critical place between 2000 hertz or 2 kilohertz and 3 kilohertz. Look at where the female voice is versus the male voice. That's one of the keys there. The female voice seems to fit much better inside the highest density harmonic content inside a traditional SSB filter, because we have 200 to 3 kilohertz, actually 200 to 3150 kilohertz is the key place. So here's the takeaway from this whole thing. The power of a given voice does not equate intelligibility. Okay? The idea that just because a person has a booming voice, those manly guys like Ernie Anderson that used to say the Love Boat, doesn't mean that voice is easy to understand in a noisy medium like amateur radio. The key to intelligibility is tailoring the content spectrum to channel conditions. That's the key of that. So now let's define what a voice channel is. The bandwidth of available transfer the intelligence, blah blah blah. I could read this from now to infinitum, but that's what it is right there. The key to it is bandwidth. Does anybody know about Heinlein here? Anybody is a Heinlein aficionado knows what Tonstoffel is? There ain't no such thing as a free lunch. Okay, every place that you've got is bandwidth. It doesn't matter if you have infinite bandwidth. There's no such thing as infinite bandwidth. The bandwidth is the key. How to move data through that little pipe that you got to deal with. Here's the voice channel. Back when I was a kid, when we listened to a long distance call. I don't know if you guys remember this or not. Did you used to remember it sounded like sideband channel, like chatter, like Donald Duck, and then sometimes you get the growl at the lower end. Well, back in the old days, what the Bell Company did is they took voices and telephone circuits, and they multiplexed them into a wire, and each one had different frequencies, and they were 4 kilohertz wide, with it supposedly from 3.4 kilohertz to 4 kilohertz as a guard channel, so that they wouldn't splatter over. But the levels were the critical thing, and a lot of the times they splatter over, but we would hear the what sounded like Donald Duck, which is somebody above you, and growling is somebody below you. And I was always wondering how that worked and why that worked. And later on, when I learned more about this, I found out what it was. But what we have here is a voice channel. We defined a voice channel in the voice bandwidth of 300. Not correct. What that
Maybe it
is
would,
the U is the frequency coverage of U, O, A. Notice how they move up.
and
E
there's a
and
gap.
I.
There is a gap in there.
No, it's like the coverage. Maybe I should have extended it all the way across. That's what it
That's
should be.
okay. That's what I was getting at.
Yeah, it should be extended across. It goes from the one on the left goes to the one on the right. That's what they do. So anyway, gee, it looks just like this. So here we go. I'm just a poor guy. I just have cable. I don't have fiber. Anyway, if you take a look at this in the composition of the voice, if you take a look at this, where have I seen this before? Well, if you just set your equalizer, on the right hand side, the same as this, you're halfway there. Okay, so if you just do this, don't do nothing else, you're halfway there. You're going to notice a dramatic increase in intelligibility in the HF bands. Why? Because you're concentrating the amount of power in the places that are going to make your intelligibility go through. That's the key. It don't matter what it's going to not going to sound like Ernie Anderson talking about the Love Boat. You know that announcer, the Love Boat. It's not going to sound like that. We don't care if it sounds like that. All we care is that somebody hears 595. That's the key. So, and as you see, there's a difference between female and male voices. And amazingly enough, if you take a close look at this, female voices are like much flatter in power spectrum, and their harmonic content falls right within the SSB bandwidth of a peak, with a peak at 3 kilohertz. So as far as women are concerned, they have a better chance of getting through between 200 and 3.1 kilohertz than we do. So that's why when you
And
hear XYL on the air, you can hear the difference.
yeah, we've all noticed that.
And this is if you look at the slide, that's the reason why. Because look at the peak on the 3 kilohertz. Their voice peaks right at most women. Their voice will peak right at 3 kilohertz, where males are going to peak about 1.5, 1.9 kilohertz. And conversely, that's why a 1.8 kilohertz filter works on single sideband better with male voices than they do with female voices. Because if you set a 1.8 kilohertz filter on female voices, you lose a whole bunch of stuff, so you don't hear them. So if you hear that, experiment with that, and you might find that this is a key to figuring out why things work in the way they work. So let's move on there. This is the core giveaway. I'm going to move a little quicker here because I don't want to keep you guys here all night. But the key to intelligibility is tailoring the content spectrum to channel conditions. That's the key. We are transmitting into an extremely noisy medium here on ham radio. It's not it's not FM broadcasting. It's not a CD. It's nothing like that. It is noise, crap, all kinds of junk. It's the neighbors' solar panels, all that. All that's going to hurt you. So the key is you don't want to, sound like Ernie Anderson. And have wide dynamic range. You want to concentrate your audio, compress it, make sure that it's concentrating in the frequencies that are going to help basically move that 595 across. That's all you care about. You don't care about sounding like Bela Lugosi. You want to make 595 go across right. That's the whole key. All right. So that's how you define communication. Minimum ambiguity. And what is ambiguity? Defines the communication channel's efficiency. The more ambiguity, the less efficient the channel. Ambiguity is basically adding noise on top of noise, things like white noise, like pink noise, that kind of thing. So the quality of a communications channel is only defined by the relative amount of ambiguity that affects the efficiency of the information transfer rate. Okay, not by the timbre, not by the beautiful sound of the voice, but by the efficiency of transferring information. So let's quickly define a voice channel. It's the bandwidth that's available to transfer the intelligence. I'm just going to keep it there. It always includes noise because if you're a Heinlein fan, you know that it's Tanstaffel, which means there's no such thing as a free lunch. Every bit of bandwidth is limited. Okay? It doesn't matter if you haven't, there is no such thing as infinite bandwidth. Somewhere there's a limit. And when you reach that limit, you're screwed. So the key to that is make sure that you get things to go through the pipe as efficiently as possible. Am I still on the air?
Yes.
Okay, very good. I'll keep going. Okay, so defining a voice channel back in the bad old days. I don't know if you guys remember this or not. I used to listen to long distance calls. When I would call from my dad would call from the U.S. when I lived in Cuba, and I'd hear what sounded like upper sideband chatter. Remember that? And sometimes you hear the growl at the bottom. Well, what the Bell system figured out because of Shannon's work is they took and multiplexed voice channels with different sound carriers from 0 cycles to like infinite cycles, and they would make them 4 kilohertz wide, and there was a guard channel between 3.4 kilohertz and 4 kilohertz that wasn't supposed to be covered by the modulation. Well, things being what they were, the modulation sometimes would overmodulate, and it would fall on the wrong side of the heterodyne carrier that they put in, and you'd hear that chatter. And that's one of the things that I thought that was kind of cool, and I wanted to figure out why that worked the way it did. And after I learned about this stuff, I figured out why. And the other thing that you get is that you had frequency tilt back in the bad old days. Remember, they had crystal mics. They didn't know what bottom end was. They were lucky they would get 500 cycles at the low end. So what they did is they took the old tube amplifiers and they cranked the hell out of the bass. So they tilted the frequency in such a way that they accentuated the bass to make it even. But then later on, in the by the 30s and the early 40s, they forgot that they had done that. So everybody had lots of bottom end. So then finally they figured out that that was bad. So they readjusted the tilt. But there's a lot of equipment that still has this built in because it's traditional to do it that way. So since it's traditional, you just do it cause. And that is what the things. But that's what the Bell system used to do with this particular environment. So here's what I want you to remember. The idea is to concentrate RF power within the available bandwidth. You want to fill that channel without overflowing it. Flatten the power spectrum and lift key intelligibility spectrum, thereby reducing the audio dynamic range and increase the depth of modulation. So let's define those. The audio dynamic range is the ratio of peaks to valleys. It's not to be confused with receiver dynamic range. It's basically the same idea, but you don't want to confuse the two when you're talking about audio dynamic range. The depth of modulation is the density of the audio waveform in relation to peak power versus average power. Bring up the lows, bring up the valleys in the waveform, and drop the peaks down and make them as even as possible, so you can stuff all that stuff down the pipe and be heard. So there you go. So dynamic range, audio dynamic range is the ratio of the softest sounds to the loudest, and the noise floor is the amount of noise that's in there. And believe it or you got to know that in a contest, it's the worst case noise floor ever. You got all kinds of crap in there. So that's the key to being able to move through a pileup, is making sure that your equalization is such that you're concentrating all the power into the places that you want. Am I still on the air?
Yes.
All right, very good, very good. All right, so anyway, the dynamic range of a signal is limited by the noise floor and the medium it's transmitted through, and we are transmitting into the noisy medium. This is not FM broadcasting. This is not television broadcasting where you own the channel. Everybody has a chunk of this channel, and they don't even know how wide the channel is, so they're going to splatter on you from the top. They're going to grumble at you from the bottom. The key to it is to keep your audio as narrow and as efficient as possible. Here's a key thing here. In competitive audio processing, wide dynamic range is not your friend. These voodoo guys that you can press AM and still hear a pseudo carrier in there. They're not going to be heard in the pileup. Okay, narrow dynamic range is your friend because we want transmitting into a very, very noisy medium. So here's a core takeaway. Real quick, go over this. Minimize audio dynamic range by using compression and limiting. Equalize to concentrate audio power. And does anybody know what the MDS of your ears is? Any idea? It's 120 dB. Why do CDs only go down to 122, 125 dB? Because any more than that, you're not going to hear it. So why waste the bits? That's the thing that they remember. If you're not going to hear it, why waste the bits? If you're not going to hear that bass below 250 cycles, why even transmit it? That's the key to that. So now, before we continue, let's dispel some religion. Okay, these are my comments. Okay, they're controversial, but I've come up with them through the years, and it's my opinion. But however, I also believe that those who agree with me will always sound cleaner on the air than those who would disagree. So let's talk about ALC. What is ALC? You're not going to push the ALC all the way up to the top so you can compress the audio. Don't work that way. ALC has nothing to do with compression. ALC is a bunch of capacitors that keep the current on your final amplifier from letting the final amplifier go into clipping on the peaks of modulation. That's all it is. It's way too slow. The attack and decay times are wrong. As a matter of fact, it was a suggestion by Art Collins back in the 50s, and there is no standard. Just every manufacturer implements it in a different way. So overdriving it increases IMD. It makes you splatter. It makes you sound like crap. So don't use it to manage audio ever, even though you're told by, oh, let's bounce the ALC off the meter. It gives you lots of power. No, it doesn't give you lots of power. It makes you sound like crap. Don't do it. All right? And I can prove it to you. Now, when you watch, am I still in the air?
Yes.
Yes.
Okay, very good. Watch this meter. See the ALC meter on the bottom here. This is from a Kenwood. Watch when I say, I'll say like in a normal. Listen for the word normal, and when you hear the word normal, watch what happens to the ALC meter. I'll prove to you how ALC works. Here it comes.
Hello, Radio 123. This is W4 Lima Tango. W4 London Tokyo 123. 1, 2, 3. Watch the ALC meter bouncing in the normal way of talking. The ALC meter never goes above the ALC measurement, but we still have good audio. W4 Lima Tango testing.
Did you see what happened when I said normal?
It dropped off.
Exactly. Why did it do that? Normal. I am modulating that transmitter with a basically almost a sine wave. And I'm going into the peaks of the amplifier, and what is the ALC doing? It's a bunch of capacitors that are giving current to the final amplifier, and there's only so much current that can be stored in the capacitor. That specific capacitor, whatever the microfarad capacity is, I don't know, who knows what it is, but it ran out of current, and when it ran out of current, you clip. Uh-oh, something happened on my screen.
Just a comment, chat comment from Ken.
Oh, okay. And I don't see those, and I don't want to press the button because I might get off the air.
Yeah.
So we'll cover those
forward.
later. We'll cover those later. But that's what ALC does. So, let's go back. Preview coming attractions here. If you remember one thing from today, ALC was not designed as a way to avoid running out of power supply current in a transmitter. It's not a compressor, so don't use it as such. Okay. I don't feed ALC voltage to my amplifier. If my exciter is clean, my amplifier is going to be clean too. Okay? So correct the exciter first, then worry about the amp. If the exciter is clean, the amplifier is going to be clean. So that's the key to that. Because remember, turning the knobs up to 11 is only good for the spinal tap. So, so if you're my age, you know what spinal tap is, maybe. I don't know. But anyway, it's supposedly a joke here that some people get and some people don't. All right, so let's move on.
This one goes to 11.
There you go. So how do you make the magic happen? Well, it starts with good as a good microphone. It continues with a good microphone technique. It's reinforced with good environmental acoustics. It's accentuated by good AF and RF grounding. Managed by attention to audio detail, especially in your DVK recordings. I'm a stickler for that. You can't tell the difference of my DVK and my real voice on the air. And I spend an inordinate amount of times making that happen. And maybe I shouldn't, but it's just a part of pride that I have in making my audio sound good. Because the key is it's both a science and an art, and it requires giving a damn. Okay, it really does. You need to concentrate on making sure that you have pride in your signal. So, first thing we should learn is how to choose the microphone. Are we still online?
Yes.
All right, very good. How to choose a microphone? The more expensive isn't always better. I laugh at these guys with the $500 TLM49 Neumann microphones. Those things are almost $1,000 in some circles, and they're using them on hand radio. And I can have my $10 Walmart headset sound just as good. But anyway, dynamic versus condenser, bias level differences. Condenser, you're going to probably need to either have a battery to feed the bias voltage to it or have the radio provide it. If you have an ICOM radio, 9 times out of 10, it's going to be a condenser mic. If you have a Kenwood radio, it's going to be a dynamic mic. Articulation. What is articulation? That's a low interphoneme distortion. It's when the microphone reproduces your voice, it has basically low IMD between low frequencies and high frequencies built into the capsule. That's what articulation means. That's a term that's thrown around by Bob Heil, God rest your soul, and nobody understood what it was. Anyway, different frequencies arrive at the diaphragm at different times and with different power. So frequency response is always an important thing, and how reflective your environment is. I always cheat with that because I basically I'm in a corner, but I also have felt on my walls. Not these walls, but in my real shack in the garage, there's felt on the walls in the corner, so I don't get minimum replacements. Because I can tell you, if I'm sitting in the middle of this V that I'm sitting in here, if I move back and forth, you could probably hear the difference in the comb filter type of response. You hear that? You probably can hear it. I don't know if you can hear it or not. I hear it in my headsets. You can hear the difference in the timbre, and the high frequencies and low frequencies are cut off and moved around because there's comb filter effects of different frequencies reflecting from the wall back into me. So anyway, you pick a microphone that has cardioid pattern because that keeps the crap from the back of it bothering you in the front, and try finding something with frequency response that fits your voice. Any real quick questions about this? And I'm still on the air.
Yes,
I
we're
have
still
one.
on.
Okay, very good. All right. Okay, I'll keep going here. So I like headsets. Okay, you saw me. I wear them all the time. I've been wearing them for 42 years. There's young me there at the control room at a television station and old me at the NAB with wearing my headsets. Okay, the microphone's always at the right distance from your mouth. That's a key thing. And they have tight cardioid patterns to help with room noise. And since you move your head around, I'm moving my head around back and forth now, you can't tell because you can't see me. And B, my microphone doesn't move from the place. You can have a boom microphone. That's really nice, but it gets in the way a lot of times. So I think headsets are a good idea. So let's talk headsets here. I have one. This is a thing that I spent $200 on. It's a wonderful headset. It lasts a long time. It was really clean and sounds good. If you're a baritone, it works real good. It has a removable cord. I've had it for about 15 years. I can't kill it, so that was a good investment. But maybe not for you. And here's the reason it works for me. Take a look at the frequency response of this microphone. Okay. Ooh, look at that 200 hertz, and it's dropping off by 1 kilohertz. I'm a baritone. That's kind of accentuating my low end. And also, take a look at this right here. 1 kilohertz, we got a real nice notch. See the notch in the middle of that? That's a 1 kilohertz. That helps with reflections from the back. All right. So that's fine and dandy. You want to spend $200 on a headset or one of those Heil headsets, that's fine. But there's no magic in it. You can spend $60 and get this. By the way, this is the microphone that you're listening to right now. It sounds really good. As a matter of fact, when I was the first time I used it at an SBE Zoom, they was wondering, what kind of microphone are you using? Boy, that thing sounds really good. Well, the nice thing about it is it's ruler flat, and the K3 really likes that. The equalizer in the K3 and equalizer in the Flex really like that because I can make this thing sound like anything. So it's also known as the COS SB40 or 45. They don't make this Yamaha CM500 anymore, which is too bad. And I've got 3 of them. So hopefully they'll last for a while. This is my favorite microphone here, Pro 8 HEX. It's set $80. I was a drummer, so I could sing at the same time that I was playing drums with this headset. There's no earphones. I have these little in-ear things, the IEDs they're called, by CCA. They're made for musicians, and they work really good. The key to this capsule is really good articulation. It's a really clean capsule. I've had maybe 10 of these microphones in the past 40 years. They don't last forever, but they're wonderful headsets. But anyway, I like them. HK3 Charlie, if you've worked him, I convinced him to buy one of these, and he will not give it up. And this is why. Take a look at the frequency response of this one. Wow, look at the boost at right around 3 kilohertz. This is a wonderful mic for this kind of thing. And it's a real nice skull shaped cardioid pattern, which keeps the crap out from the back. So this is things you need to look at when you choose a microphone. It may work for me, might not work for you. You don't know. And really, you can spend $10 on a headset and still not sound better than $1,000, $2,000 microphones. It's with today's transceivers and their equalizers, you can make probably any crappy mic sound pretty good. So the key to it is experiment to find something that fits your needs and voice. My wife always bitches at me. How many headsets do you really need?
One more.
I always need. It's like handy talkies to the Shack on the Hip guys. How many handhelds do you really need? If you only have one hand and you have like 15 handy talkies, why do you need so many? Well, because you get to play around with different stuff. You experiment and find someone needs with the voice. And like I say, I like the Yamaha headset, and I like the Audio Technica headset. I used to own Heil headsets. I don't want them. I don't like them anymore. They don't work good with the newer radios. So, mic technique and acoustics. Talk across the mic. It's what I'm doing right now, not directly in, because you don't want to pop your P's like that, right? So, talk across. Try not to close talk electric microphones. Why? Take a listen to what happens if you close talk an electret. This is an electret being close talk now. You hear the distortion, how bad it sounds? And we're going to back it away. Now, one of the things with dynamic mics, if you guys remember back in like 2016 when there was what is it, Hillary Clinton and Trump had a one of those whatever you call things debate, right? And they were using these little electric microphones, and Trump was always complaining, and he would like try to close talk it, and it would go into distortion. Okay, do you notice the microphone he uses now? It's an Electro Voice. What is it? Yeah, it's an Electro Voice SM580, I believe it is. It's a drummer's mic. You can be right on it, and it gives you lots of bass because he really likes to have that bottom end to his voice. Because if you look at the difference between him, Obama, and Biden, Biden and Obama both are baritones. He's more of a tenor, but he wants to have that bass to his voice. So that's why he uses that SM58 microphone and talks right onto it. You'll notice that now after he gets in the office, all the microphones and all the podiums are going to change, and they're all going to be SM58s. It's That's the key to picking the microphone that works with your voice. That's the key to that. So anyway, try not to be close to hard walls. Cover with felt curtains like I do. Desk in the corners of hard wall rooms are challenging, just like I am right now, right here, because you get the comb filter effects, because you sit in the middle of a corner reflector. And the quieter the room, the better. Yeah, turn on your amplifier blower. That's how it works. So far, any questions with this? Anything that I can answer real quickly, and then we'll move on? All right, fine. Let's move on. Here's the key to what we're talking about here, using your tools at hand. Here's my voice. Here's what I sound like clean, and I hate my voice because it's too high.
CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango. CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
Okay, you hear that hiss in the background? We're going to deal with that hiss coming up next. Next thing we're going to do is we're going to apply gating or downward compression, some people call it. What does it do? It mutes the noise after the audio pickup, reduces wasted bandwidth, and smoothly manages the transition from silence to full power. Early K3s did not have this. They went from like no gating to maximum gating like instantaneously. And I had a big discussion with Lyle, KK7P, I think is his call sign. And he finally said, okay, I'll ramp it for you. Stop complaining. And he did. And it sounds much better. So you want to put the gating as close to the microphone as possible. This is what it does. Listen what it does to the noise.
CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
Wow.
CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
You hear that? How it gates the noise off? We're not going to waste bits on noise. You know, bits are expensive. We don't want to waste it. So the next thing you have to do right after gating is you apply your equalizer right there. Why? Because what we're going to do is we're going to compress and limit only the frequencies that we're going to deal with, only the frequencies that are important to us. So that's why we're going to put it where we put it. And you can read this, not a problem. Rearrange the power ratio, blah, 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 you know, immediately after gating, but before other processing. And it will do this. That's the curve that I'm setting for myself. And I'll tell you why that curve is that way in a little bit. Listen to the difference after I equalize.
CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango. CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
Did you hear the difference? How there's very little bass here, how it's like crackly sounding, how it has lots of punchy high end. That's what we want to do. We want to maximize signal to noise ratio by managing our frequency response and only dealing with the frequencies that are going to help us move communications around and have other people hear our exchange. That's the key. Now we're going to do, after that, we're going to apply compression, because what we want to do is we want to bring the valleys up. We want to bring the peaks down and clip them off. We want to increase the modulation density so that we can take advantage of every watt of power that God gave us, for God's sakes. And I usually run, you know, no more than 500 watts. And I think I do pretty good with it. Here's what it would sound like after I do I do some compression.
CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango. CQ Contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
You hear that? See how dense that modulation is? But then again, our peaks are still too high and our valleys are still too low. So what we want to do then is we're going to apply limiting. We're going to clip the tops of those waveforms. Now, every time you clip something, you create square waves, which is a bad thing. So use it in moderation. Don't overclip. Most processors now in radios are clippers and not compressors. The cheaper radios have compressors. Things like the Yaesu FTE DX 101s and stuff like that are more digital RF clippers. K3 is a clipper. K4 is a clipper. And there's some other magic in Flex, which I'll talk about later. But clipping is always placed after compression. So keep in mind, a little bit goes a long way. Use in moderation. And here's what it would sound like. And notice, take a look at the waveform. See the difference? See where the red arrows are at the bottom? I got rid of all that noise. I got rid of all that overshoot. And I've compressed the sound, and I've clipped off the top of the waveforms so that I have dense modulation. And here's what it sounds like.
CQ contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango. CQ contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
Does everybody hear the difference between the first one and this one? Okay, this is just simple stuff that I've done inside a computer. And that's how much it changes. So what are we trying to do? We're transferring intelligence within 3 kilohertz. That's all the bandwidth we got. We maximize intelligibility with our bandwidth constraints, reduce the frequencies that ineffectively transfer information, use as much available power as possible to transfer information, and use all available means to increase the signal to noise across all formats and vocal spectra. And go back in the thing and see slide number 10 chart, which looks like this. Then this is what we're doing. We're lifting that. We're flattening out that tilt that we have in most audio frequency responses in radios today. So what's it sound like through the transmitter? You see this thing right here? Let me go back up there. See that right here? See how the tilt's down at the top? Watch what happens to the transmitter after I do all this processing.
CQ contest, Whiskey 4 Lima Tango, W4 London Tokyo contest. CQ contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
Okay, do you see the difference there? What I'm trying to do is lift the high end and keep the low end where it's at, but bring the ratio of peaks to valleys up. Okay? All right, so am I going to sound like Ernie Anderson? No, but it's going to get the information through. Listen to this pilot. That's not a pilot, but listen to these 2 signals and see which one you would answer first.
K4, Mike India. Okay, K4, Mike Italy, 5914. 5905. Thank you, GW4BLE. Whiskey 4 Lima Tango. Whiskey 4 Lima Tango, 5914. 5905. Thank you, GW4BLE. GW4 Bravo Lima Echo, contest. Whiskey 4 Lima Tango. AW4 Lima Tango, 59837. 837, thank you. 59065. Great, GW4 Bravo Lima Echo.
Did you hear me competing with that other signal? Who won? I won. Why? Because I had audio that people could understand, and the other guy did not have understandable audio. That's the difference. That's why this works. What's the point? The idea is to be heard and understood. We only have 3 kilohertz. We're transmitting in a noisy medium. We got to adapt it because every voice is different. SSB is not a place for ESSB or wide dynamic range audio, and all things in moderation. Knobs 11 are only good for spinal tap, not hams. Be gentle. A little goes a long way. Okay? So here's the point to it. I have 500 watts maximum. In this case, it's 100 watts on 15 meters with this crappy little antenna at 40 feet. Listen to this pileup.
Whiskey 4 Lima Tango, contest.
Lima Zulu 9 Whiskey.
Lima Zulu 9 Whiskey, 59 Fox Lima.
59 Kilo, good luck.
Thank you.
Oscar Kilo 2 Kilo Juliet United.
Oscar Kilo 2 Kilo Juliet United, 59 Fox Lima.
US 59 Kilo 1.
Thanks.
Yankee Papa 8 Tango.
Yankee Papa 8 Tango, 59 Fox Lima.
59 Kilo 1.
Thank you, W4 Lima Tango.
Sierra Victor 5 Delta Kilo Lima.
Sierra Victor 5 Delta Kilo Lima, 59 Fox Lima.
Roger 5959.
Thank you, W4 Lima Tango.
Delta Lima 8 Bravo Papa.
Delta Lima 8 Bravo Papa, 59 Fox Lima.
59700.
All right. I built that pileup with this crappy antenna, 100 watts on 15 meters, and I had like 4 or 5 station deep pileups. Now, I live for this kind of stuff. I live for these pileups, and I don't get them that often. But I think my audio frequency. This was recorded by somebody at the Tampa Club down the street from my transmitter, so it's an off-the-air sound there, and that's the whole point of this. All right, so that's it for that. let's go over a few magic things called new technologies called control envelope, single sideband, and adaptive pre-distortion. Am I still on the air, by the way? I think I am. Yeah. Okay. Very good. All right. So these things are new to hams, but they've been around for a long time. Especially the adaptive pre-distortion. So what is a pure signal? You hear this thing, pure signal. Well, it's a concept that's been around since the 60s. I remember an RCA transmitter that I worked in when I worked at WPGH Pittsburgh. We had this box called a Datatech, and it was a bunch of resistors and capacitors. And what we did is we screwed the video waveform up going into the transmitter so it came out right on the other side. That's all adaptive pre-correction is. Okay, it's much easier now with SDR and DSP. And I first saw it on an ADAT 200. And I said, "Geez, where have I seen that before?" So, what does it do for you? Well, you take a look at this. This is without. It's an S9 plus 20 signal. Look at the edges. Look how it spreads out. Look how it's kind of mushes around. And here's the same signal, same level with pure signal. See what it's doing? It's concentrating the power just in where you need it, and makes you a good neighbor too. You don't splatter over everybody. It gets you nice and clean signals, and that's a good thing. Also, see it reduces the IMD. You can see in the picture on the left-hand side how it's spread out like that. That's our intermodulation products on your transmitter, and on the one with pre-distortion, they screw up the signal going into the transmitter so it comes out right, and you got these nice even edges.
Hey,
Makes it
Lou,
work really good. Yes.
a better way I think to explain it is they figure out what the distortion in your radio amplifier chain is.
Yeah.
And they compensate for it by inverting it. And that's why you don't have the IMD and the wider signal. And the wider signal is bad for you because you're not putting energy where the other guy's going to hear it because his filter is going to take it out.
Exactly.
Putting all the energy where he's going to hear it is much better for you, for him to understand you.
Exactly, and it leaves you have more bandwidth for other people to get in there as well. That's if everybody had this, the bands would be much cleaner, and you could get more people on. And that's another positive thing about this, but not everybody has it, which is a shame. But anyway, that's what pure signal is. Now,
well, just wait 10 years.
Yeah. Now let's move on to another one. This is one kind of like my favorite. It's called Controlled Envelope SSB. All right. It was developed by David W9GR. I've known him from Harris Broadcast. He was one of the transmitter wizards that sit in the back room and built crazy stuff that we'd go out and explain to other people in small words and single sentences. I was skeptical. This flex crap. That's another marketing thing. It's another processor. Then I tried it, and I was very impressed. It's a different way to generate SSB, and it's really, really close to pure signal in a single-ended process. Is it? I look at it as a technical miracle because any advanced enough technology is indistinguishable from magic, and this stuff is magic. It really does. Makes my 500-watt amplifier sound like a kilowatt. Really makes the meters dance, and I can prove it to you. All right. Here's a conventional SSB with 59% overshoot and clipping. I can clip those, but every time I clip them, look at the one on the right, that square wave on the right. See those two little things that stick up? That's clipping products. That's intermodulation distortion products. Okay, that doesn't help you because that doesn't help get the information through. So if we put this thing through CSSB, same signal. Okay. The one on the right-hand side is through CSSB. Look how clean that is. We only have 1.6% overshoot. So we're, again, using every watt we've got to move information through in a clean way. Notice the square wave. There's no ringing. There's no overshoot. That's a good thing. So you say, oh, that's bullshit, Lou. Really bullshit. I can prove it to you. Let's watch the average meter on this amplifier without CESSB and then with it CSSB. Notice what happens to the overshoot. I'll light some red lights when I modulate with this one, And watch the difference between the 1 and the 2. This is without CESSB. Watch the meter.
Whiskey 4 Lima Tango, Whiskey 4 Lima Tango, contest. Whiskey 4 Lima Tango, Whiskey 4 Lima Tango, contest.
Okay, you see how the difference between the lights that are all lit and the ones that flash at the top. Okay, that's my dynamic range. Now I turn on the CSSB, same amplifier, same setting, everything's exactly the same, and look at the difference.
CQ contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango. CQ contest, Whiskey 4 Lima Tango, Whiskey 4 Lima Tango.
You see the difference? That's 500 watt amplifier sounding like a kilowatt because of the depth of modulation. It gives you about 80% more, 3 dB, without added distortion. Magic, true magic. Read the paper. It's really incredible what this guy designed. And it just, I mean, I'm totally impressed how it works. It's got a lot of mathematics in it, so be careful with it. But it really is an impressive solution to a lot of things. Elecraft has now adopted CESSB on the K4, and Flex 6000 and 8000 series has CESSB. I think it's the only ones that have implemented to now. But it's really a cool thing. So, in closing, don't be this guy. Look at this waveform. Look at the way this guy sounds.
Whiskey 4, what's up, Charlie Zulu, 4943?
First of all, I guarantee you that's an old ICOM by the looks of the IMD on the bottom end, on the other side of the upper sideband, on the lower side of the carrier.
Lots of reverb. Sounds like he's in a stairwell.
Yeah, yeah, and you can't understand what he says because he's all distorted and all crappy. Now listen to the difference and listen to this guy.
Whiskey 0, Zulu Alpha Papa 59327. QSL 145, thanks. Victor Alpha 7, Sugar Tango.
This guy's gorgeous audio, gorgeous contest audio. Okay, I've worked him a couple of times and I always compliment him. He always sounds this good, and we all should sound this good. And it's not hard to do. It just takes caring and giving a darn and making sure that everything is set correctly.